A heavy launch vehicle clearing the pad represents millions of parameters executing in real time. Tracking its absolute trajectory relies on a single mathematical variable. In early undergraduate calculus, the constant of integration, plus c, is often treated as a minor bookkeeping requirement. It is the letter tacked onto the end of an indefinite integral to avoid losing points on an exam. This equation separates abstract theory from applied engineering. In pure mathematics, plus c generates an infinite family of parallel curves. In practice, it anchors our calculations to the physical world. You cannot recover a system's absolute state solely from relative rate of change data. You need an initialization anchor. We can trace this specific mathematical requirement across 3 distinct domains: aerospace telemetry, electronic circuits, and computing architectures. The constant provides the necessary initialization that keeps physical and digital systems synchronized with reality. This coordinate plane plots 3 identical parabolic curves, each shifted vertically along the y-axis. Differentiation is lossy with respect to absolute static position. Taking the derivative of any constant value yields 0, stripping away the starting point. When derived, all 3 parabolas collapse into a single identical linear slope. The original y-intercepts are erased. When measuring a live system, we often only capture this resulting output, the rate of change data. Reversing the operation via integration returns the trajectory, but the absolute static reference baseline is unrecoverable from the rate data alone. This missing vertical translation is what plus c represents geometrically. Every curve in this infinite stack shares the exact same slope trajectory at any given coordinate on the x-axis. The math alone cannot tell you which curve represents the current state of a system without outside intervention. This geometric abstraction maps directly to aerospace telemetry. This is a schematic for a rocket's internal accelerometer, governed by the velocity integral. Onboard accelerometers have a limitation. They only measure instantaneous axial acceleration over time. To calculate the vehicle's relative velocity profile, the flight computer integrates that continuous stream of acceleration data. Within this domain, plus c maps directly to the initial velocity state of the vehicle before tracking began. Consider a rocket stationary on the launch pad compared to a second-stage rocket igniting while already traveling at Mach 1. The raw acceleration graph recorded from the moment of ignition looks identical in both cases. Without initializing the boundary value to represent the starting condition, the acceleration data alone cannot determine the absolute current velocity of the spacecraft. At the microscopic scale of electronics, raw electric current violently rushes forward, flooding into a tightly confined physical space. This diagram outlines a standard decoupling capacitor, a physical component reliant on this integration equation. The current entering the capacitor defines the instantaneous rate of change of the voltage across its internal plates. Determining the actual voltage requires integrating that incoming current waveform over time. Here, plus c, is the initial residual voltage trapped across the dielectric substrate prior to time 0. The current waveform dictates how the voltage will change, but the absolute voltage level is dictated by this initial state of charge. Predicting circuit behavior without accounting for the residual substrate charge results in a failure to model the system's actual performance. The exact same mathematical requirement applies to modern data centers, where millions of digital transactions flow continuously in real time. High-throughput software architectures often use event sourcing and ledger accumulators to manage this volume. This flowchart illustrates an event sourcing database. Instead of storing absolute account states, it records an immutable stream of transaction deltas, like plus 100, minus 45, or plus 20. To calculate an account balance, the system processes and sums these changes over time. In this architecture, plus c represents the genesis snapshot, or the initialization seed balance. The delta stream records the modifications, but it possesses no context of its own total scale. You cannot deduce an absolute user account balance without anchoring the transaction stream to that original baseline constant. We can use a software verification engine to analytically demonstrate how this single constant functions across all 3 domains. This Python script utilizes the SymPy library to calculate the indefinite integral of a custom polynomial expression. The SymPy output calculates the base mathematical trajectory. It gives us the shape of the data, but it lacks a starting point. This visualizer uses matplotlib to plot that trajectory, generating the vertically shifted family of curves we analyzed earlier. This top curve represents the aerospace telemetry model, anchored by an initial velocity of Mach 1. This middle curve maps to the electronics example, anchored at a 5-volt residual charge. And this bottom curve illustrates the computing architecture, starting with a $100 Genesis seed. Analytically, math outputs the base trajectory, but applying that trajectory in reality requires mapping it to a single real-world state. Calculus tracks how systems change, but engineering requires these boundary conditions to define where those systems actually exist. Every system we've examined, from rocket velocity to database balances, requires this specific initialization value to turn raw rate of change data into a measurable reality.